Welcome to the second video on elementary data structures. So we have seen so far abstract data types and data structures. We have seen stacks and dynamic arrays. Now we're going to see a new abstract data type, namely queues, and linked lists as a data structure implementing queues and also implementing stacks. So what is a queue? A queue stores elements, and whatever goes in first should also leave first. So it has a first in, first out scheme. We're storing elements. We want to support insertions and deletions, and we delete the element that was inserted first. In terms of operations, that means we have insert and remove, which here are called enqueue and deque. So enqueuing an element means we're inserting it. Dequeuing means that we remove that element and return it. Just like for stacks we had push and pop, we now have enqueue, deque. And we also again want to be able to know the size and whether a queue is empty. So let's see how it works with what we already know. And what we already know are dynamic arrays. So dynamic arrays can actually be used to implement queues. But we have to be a bit careful. So imagine we're using an array, and let's say a dynamic array, to implement a queue. So we're inserting elements, and then when we delete elements, we want to delete the element inserted first. So if we insert from left to right, what it means is that we start by inserting here. And let's say this is a number of times we already inserted so far. But whenever we delete, we don't want to delete from here, but we want to delete starting here. So that means we're going to also delete from left to right. What does that mean? It means that we don't only need to take care of where can we insert next, which is here, this tail, but we also have to take care of where do we remove next, which is this head. Let's assume we insert 4 more elements. If we insert 4 more elements, we run out of space here. So we're doing dynamic arrays, so we could resize, but that would not be quite as efficient as we would like to have it. Because what that means is that we could have only one element in our queue, but still, and a huge array, but still resize just because that element is currently stored at the end. So what we can do instead is we're going to wrap around. So how does that look like? It means that if the tail hits the end, it simply starts here at 0 again. Yeah, and this way we can use our space efficiently. So we only need to resize whenever the tail bites the head. So how would this look like if we want to, so deque is easier. If there's nothing in the queue, then we should raise an exception or give an error. Otherwise, we report the element that is currently at head and increase head by 1. We're doing this modulo the capacity. What does that mean? It means that if head currently points here, and we increase it by 1, it would now point to a cell that is not actually there. But if we do modulo the capacity, it means that if we step over the capacity, we again start at 0. So increasing by 1 and doing modulo doesn't bring us here, but brings us here. And that's exactly why we do it like that. And if we deque, we also want to reduce the size by 1. Enqueuing, essentially very similar, just in case we hit the capacity in terms of our size. So if there's no space, so if the tail is really here at the head, then we resize. So then we double the size of the array again. We copy everything to the new array. And obviously when we copy, we don't need to keep the head here, but we simply can start again with the head at 0, just to make things simpler. So that is a queue implementation using a dynamic array. So let's assume you want to use a queue and you want to use it in Python. So in Python there are queues, and they are actually called deques, and that stands for double-ended queue, because you can insert and delete at both ends. They are provided in collections. And yeah, here's an example. So I can create a deque with elements 2, 3, and 5. And if I do append, it will append at the end. After the 5. If I pop left, so there's also pop right because it's double-ended. Pop left would remove the 2 and return the 2. But a deque is not implemented using a dynamic array. A deque is implemented by a doubly linked list. So that's a different data structure, which we're going to see soon. Of course, you could also use the idea of dynamic arrays, but you have to be careful. First of all, you would have to do it by hand, but also you have to be careful. The enqueue is easy to just append, and that takes amortized constant time. More or less, you also have this issue with there might be very few elements in there and simply head and tail moving together more or less. But what about dequeuing? So let's assume instead of doing this trick with head and tail, we do simply pop 0. Yeah, so this would be a naive implementation of a queue using a Python list. So this naive implementation, how expensive is the pop? So what's the running time of pop 0 on a Python list with n elements? Is it constant? Is it amortized constant? Is it order log n, or is it even linear? The running time of pop 0 is linear, and the reason being that if you want to remove the first element in a Python list, which is the same as removing the first element in an array, you do so by shifting all other elements and shifting all other elements, so copying the elements one by one position forward. That is linear time. So this is something that you do not want to do if not necessary, and it does not provide an efficient way of implementing a queue. So you can do the business with the tail and the head, so that's efficient, but don't directly use pop 0. We're going to see an alternative, and that is implementing queues using linked lists. So linked lists are very simple data structure. They consist of nodes. And in a singly linked list, and the single comes from this link here. So a singly linked list that has nodes which can store an element and have a reference to the next node. So you can think of this as a sequence of nodes. It has a start, and the start is the head or header. So the head gives me this node here. And then every node stores an element. So maybe this one stores A and has a reference to the next node. How does this look like, for instance, in Python? We need objects, node objects, and list object. So S here stands for singly linked, a node in a singly linked list. And as such, as a method, we here simply have to initialize a node. If we have an element and a next given, a next node given, we store that element and we keep track of that next node. And then a list is simply a sequence of such nodes which we store by remembering what the head is. So a list only knows the head, and from there it can find all other nodes because we have those references to the next node and so on. Let me give you an example. So this is a very basic linked list implementation. You can of course implement more operations when needed. So here's an example. So we have this node 3. So let me draw this node 3. So we always had these nodes. I put the name on top here, node 3. It stores an element, in this case a string called Toronto, and it doesn't have a next, so next is none. Now I'm creating a node 2 which stores Seattle and as next has node 3. So how does that look like? I have node 2 here. It stores Seattle. And the next is node 3, so it points here. Then there's node 1. I'm creating a node 1. Let's have it here. Node 1. It stores Rome. And its next pointer, it points to node 2. And now I have a list. And my list has a head. And that head, I simply say, is node 1. So with this, I create a very simple singly linked list. And now if I want to, for instance, print all elements, what I can do is I start at the head, and then as long as there's a next, I go to the next and print. So I start, so the current node is the head, and the head is this one. So I start here with node 1. And while there is a current node, so while I'm not here, I print the element. So I print here, for instance, Rome. And then I set current node to the next of current node. So I print Rome, and then I say current node is actually now node 2. I print Seattle and say follow the next pointer. I'm at node 3. I print Toronto. I follow. I'm at none. So now I leave the while loop, and in this way, this is a very simple way of traversing a linked list, in particular a singly linked list. If we want to implement queues and stacks using linked lists, then we have to think about how can we insert and delete efficiently. So let's start with insert, and the natural place to insert is at the head. So why do we want to insert at the head? Because the head is the node that we have access to anyway. So how do we insert? It's very simple. First of all, we need a new node. Let's call that one, to keep things simple, new node. Any other name would do. And of course, so that's what we do here, allocate a new node, insert the new element. Let's say that's whatever it is, Baltimore. Done. Now, what we want to do is that this node points at node 1. So node 1 is a current head. So what we can simply do is we can say that the next of new node, so new node next, should be head. So the head of the list. Yeah, and this way we now point here. Additionally, we need to update the head. So we have to tell the list that its new head is simply our new node. So, and with that we are done. How does this look like in code? So we have the new node, we create the new node, we set the next of that node to the head, to the old head of the list, and then we set the head of the list to our new node. And just for testing, we print and we see that this indeed worked out. How do we delete? That's very simple. At least deleting at the head is very simple. So let's say here we want to remove the first node. So the node was Baltimore, this one. The only thing that we need to do is to update the head. So the head now should, in this case, be again node 1. So how can we tell the head to be node 1? We just look at the old head, look at its next node, and whatever that is, we're going to set that to head. So we're going to set the head of the list to the next of the old head of the list. And in this way, remove the first element. Let's have a quiz, namely the following. How long does it take to insert at the head? So remember how insertion worked, and then answer constant, order log n, or linear time. The correct answer is A, constant time. And just as a reminder, what did we do? We created a new node with a new element. Now we looked at what was the old head. That would be the next node from our new element, and then we would update for the list the head to being the new node, and that was everything we did, and that we could do in constant time. What do we have so far? We have single linked lists where we can insert and delete at the head. This means that we can already use them to implement stacks. So not queues but stacks, because for a stack we wanted to be able to push an element, and we wanted to be able to pop the element that was last pushed. So if we do all of the insertions and deletions at the head, we exactly get that. And in this way, we can use singly linked lists to implement stacks efficiently. Efficiently meaning that to store a linear number of elements, we need linear space because every node takes constant space, and the operations take constant time. So the operations being push and pop, which corresponds to insert, delete, and then we can keep track of the size and whether the linked list is empty. And now you could put all of this in code. So this would be a stack implementation using a singly linked list, and all of the ingredients that you see here we've already seen. So this is simply another parameter count which keeps track of how many elements we have. Otherwise we simply have a list, and that list has a head and it works with nodes and so on. Now that's a stack based on a singly linked list. How about queues? So what's the problem? The problem is that if I want to have a queue, then I should be, for instance, inserting at the head but deleting at the tail, or deleting at the head and inserting at the tail of my singly linked list. Can we do that efficiently? So let's have a look at the option of deleting at the head and inserting at the other end, the tail. So we already know we can delete efficiently at the head. So can we insert efficiently at the tail? So at the end of the list, linked list. We have to be careful, because to be able to insert at the tail, we first have to be able to access the tail. Now, if I only have access to the head, the only way to get the tail is to start at the head and move through the list. That already would take linear time, so that we want to avoid. We can easily do so by also simply storing the information about which node is the last node. So what's my tail? With this, we can insert efficiently at the tail. So let's say I want to insert a new element a new node storing an element D. What I do is simply I make this node with the element. So I make a node, it stores my element, let's say it's D, and it will point at none, or nil, or null. In Python it would be none. Now we know what the tail is, the old tail, and the next pointer of the old tail, so this one here, should now point at my new node. Now the only thing that remains is to update the information that my new node is a tail, and now we've inserted another node. All of these operations took constant time, so inserting at the end takes constant time. That allows us to get an efficient implementation of a queue, where we do the enqueue, so the insertion at the tail of the list, and the dequeue, so the deletion, at the head. So that gives us linear space, constant time operations. Great. And again, we could put all of this into code, and this would be an example. So this is an example of the from the corresponding notebook that we have. Now let's look at one more operation, and that is removing at the tail. So can we remove efficiently at the tail? So first of all, of course, to do so, we want to be able to point at the tail. That we can do. But now there's a problem. I want to delete this node. What do I need to do for that? I would need to update the information for the tail, the information that it should be pointing here, and I should update this pointer to none. But how do I get node D? Or the node that stores D. How do I get this node? There's actually no efficient way of getting this node. Because the tail doesn't, it's not the previous tail, and the previous tail doesn't know this because all nodes simply point to the next one, not to the previous one. So the only way to access D is actually to start at the head and move to D, but that is linear time. So in a singly linked list, deletion at the tail is not efficient. So we can insert at the tail, but we cannot delete efficiently at the tail. Doubly linked lists will solve this problem, but before we get there, let's have a quick quiz. So why do we normally use dynamic arrays and not singly linked lists when we implement a stack? Is it A, because we have lists anyway at hand? B, because in practice linked lists are less efficient? Or D, simply because people don't know about linked lists? So the reason is B, they're less efficient. That's really only the reason that there should be, and enough people know about linked lists. And the problem here really is in terms of, you could say, the constants. Obviously both of them, the operations take constant time. Even linked lists have the advantage of not needing the amortization. But you have all of these node objects, which might even be at different places in memory. And the overhead of that makes everything slower and bigger than if you simply have an array where you store your elements, which Python lists essentially do. So much about stacks and singly linked lists. Doubly linked lists. They like singly linked lists, but with 2 links per node. So we don't only have a link to the next node, but also to the previous node. That's what a doubly linked list is. So here you see a node. Previously singly linked list, we had this next. Now we also have the previous. Of course, we again store an element, and then we have special nodes at the beginning and head to mark the head and the tail. How do I insert into a doubly linked list? That is very simple. So let's assume I want to insert node D after node P, so between P and the successor of P. then, okay, I need to know P. If I have P, then I simply take my node Q. Let's say this is node Q. It again has this form. Let's say it stores X. No, so what do I need to do? I need to update. I would need to get the pointers for the node Q, and I need to update the next pointer of P and the previous pointer of the next node after P, so its successor. And that's exactly what we do. We know this next because we can get it as the old next of P. We know the previous because that's the old, because that's simply P. And now we need to update the next pointer of P to point at Q and the previous pointer of the successor of P to point at Q, and that's exactly what we do. And all of this we can do in constant time. Likewise, deletion. If I want to delete a node and I already know which node that is, then I can simply update. I can update the next of the previous to the next of P, and I update the previous of the next one to the previous of P. And that's all we do. And again, we can do that in constant time, assuming we already have P. Of course, if I would first have to search for P, then that would take linear time for searching. But if I have P, I can delete it in constant time. And then we get this. So now we have doubly linked lists. We know how to insert, we know how to delete. Let's have a quick quiz. Why is deleting the last element in a doubly linked list more efficient than in a singly linked list? A, because there's a trailer. B, because we can find the last element more efficiently. Or C, we can find the next to last element more efficiently. A, B, or C? The correct answer is C. So both in singly linked list and doubly linked list, if we want to, we can have a trailer or a tail. We called it for the singly linked list. And that gives us efficient access to the last element. But the problem for the singly linked list was that we cannot get the next to last element. But for the doubly linked list, that is no problem, because from the last element, we can simply follow the previous pointer to find that. This means that we can use doubly linked lists to give us deques, so double-ended queues where we can insert and delete at both ends. And that's exactly how deques are implemented in Python. And that gives us linear space if we have a linear number of elements and all the operations in constant time. So what have we seen? We've seen as abstract data type queues, and the first data structure that we saw that implement queues were dynamic arrays, but that was a bit complicated because we had to have this head and the tail and the wrapping around. Then we looked at linked list. We looked at singly linked list, where we were simply storing an element and the next node, and doubly linked list, where we're storing an element, the next node, and the previous node. And we saw how to implement queues using linked list. So that already was possible with a singly linked list, but with a doubly linked list, we can get deques where we can insert and delete at both ends. So what have we seen when we take this video and the previous, so the part 1 video together? We've seen abstract data types versus data structures, so functionality versus implementation, and implementation meaning how do we store the data, what algorithms do we use to implement the operations. As abstract data types, we've seen stacks and queues, and we have seen lists in Python. In terms of data structures, for stacks and queues, we've seen arrays of fixed size. Those were not that useful. Dynamic arrays, which implement the lists in Python and can be used for stacks and queues, and linked lists, singly linked lists and doubly linked lists. And to analyze the dynamic arrays, we've seen amortized analysis, where we took all of the operations, the running time of all operations, of n operations, T of n, and then divide that by n to get the amortized running time, so average over sequence running time of an operation. That's all for today. See you.